Hello everyone, welcome to this week's highlights. We're going to start talking about density, which uses the Greek symbol rho, that's this symbol here. Now density is just the mass of an object divided by the volume of the object. Let's say we wanted to determine the average density of Earth. Well, here's the mass of the Earth, and also here's the radius of the Earth. Well, to get the average density, we can just use our density equation. That's just going to be the mass divided by the volume. Now, the volume of a sphere is 4/3 pi r cubed. And so we can just plug that into our equation. So the density of the Earth is the mass of the Earth divided by 4/3 pi r cubed. And we arrive at 5,513 kilograms per meter cubed as the average density of Earth. Next, let's talk about pressure. Pressure uses the symbol P, and of course pressure is just the force perpendicular to a surface divided by that surface area. Now the units of pressure are newtons per meter squared. We can see that here, forces is measured in newtons, area is measured in meters squared. We do have a nickname for this unit, just like a nickname for newtons, and the nickname is pascals, PA. So let's calculate what the pressure is on this table from this book. So pressure is force over area. We're told that the book has a weight of 4.5 newtons, and so that's going to be our force. But now we got to get the area of the book. Now that's just the area in contact between the book and the table. So we have three numbers here. This 5 centimeters, that's just the height of the book. It's not going to give us the area of contact here. So to get the area, we got to do length times width. Now I told you in centimeters, but we're always going to keep things in meters. So we got to convert that back to meters. So we have the 0.23 multiplied by 0.35 gives us an area of 0.0805 meters squared. Then we can use our pressure equation to calculate that. Pressure is just force over area. The force is going to be the weight of the book, which is the 4.5 newtons, divided by the area we just calculated, and we get a pressure that the book applies to the table of 56 pascals. Next, let's talk about air pressure. Now, air pressure comes from these air molecules that are bouncing around, and when they bounce off of a surface, that collision applies a force to that surface. And that force over that area is a pressure. You can think about this pressure as the weight of all of the air above it. So here all the way up into space, there's a bunch of air that has a bunch of weight that's pressing down on the surface here on the ground, just like the book on the table. And that weight over that area, we can determine what the atmospheric pressure is going to be. And that's going to be 101,000 pascals, or 1.01 times 10 to the 5th pascals. This is also called atmosphere, or ATM. Now this is the number, this is the number at sea level. It'll be different at different altitudes, but for the most part, we're just going to be looking at sea level. Let's look at a pressure in a fluid now. As you go deeper into a fluid, now you have more weight of an object above you. So we have the atmospheric weight above us, and as we go down, we have the weight of water above us as well, which is going to increase the pressure that's going to be applied. So the deeper you go into a liquid, the larger that pressure is going to be. And we have an equation for that. Pressure in a fluid is equal to rho GH plus P0. Rho, again, that's just the density of the fluid. G is gravity, which is 9.8. Now H is the depth. That's the depth from the surface to where you are. And P0, that's the pressure at the surface. If this is just open to air, that'll just be that atmospheric pressure we talked about, the 101,000 pascals. So let's say we dive down 10 meters below the surface of a pool at sea level. So the atmospheric pressure is going to be the 101,000 pascals. Here I tell you the density of water is 1,000. We can calculate what the pressure in that fluid is going to be. Rho GH plus P0. Well, rho again is 1,000, G is 9.8, and the depth we're at, that's the 10 meters below the surface, plus the atmospheric pressure P0, which is the 101,000. Now we multiply and add those together, and we get 199,000 pascals, which turns out to be around 2 atmosphere. So if the atmospheric pressure is around 100,000 pascals, and this is around 200,000 pascals, this is around 2 atmosphere. So what's neat is every 10 meters down you go, you increase your pressure by 1 atmosphere. So if you go down 20 meters, now you're at 3 atmosphere, 50 meters, now you're at 6 atmosphere, and so on. For reference, 10 meters is around 33 feet. Now, this pressure being larger the deeper you go is actually going to result in a buoyant force. So if I draw the forces on this block of wood due to the pressure, let's look at the top and the bottom. So because the top part of the wood is not as deep as the bottom part of the wood, there's less force due to pressure on the top of the wood than the bottom of the wood. This results in a net upward force we call the buoyant force. If you look on the sides, each horizontal component is going to cancel each other out. So even though this is deeper, this other side's deeper as well. So we're going to have no horizontal forces due to pressure, only a net vertical force. And we have an equation for this buoyant force, and that is the buoyant force is the density of the fluid times the volume of fluid displaced by the object times gravity. Now, when the object is fully submerged, this volume here is going to be the volume of the object. But when it's floating, it's just going to be the volume of fluid displaced by the object. This is the same thing as Archimedes' principle, where the buoyant force is equal to the weight of the fluid displaced. This rho Vg here, this is just another calculation for the weight of the fluid displaced. So here we have this block of wood is now floating. We have the weight of the wood and the buoyant force. And let's say the block of wood displaces 0.03 meter cubed of water as it floats. So that's just this volume here, just the water that's displaced, not the volume of the wood, just the water displaced. And we want to know what the buoyant force is here. Well, we have our buoyant force equation, rho Vg. Again, the density of water is 1,000. So we have 1,000 times the volume displaced, which is 0.03, times g, which is 9.8. We arrive at 294 newtons. Well, what is the weight of the block of wood? Well, because this is floating at rest, the weight must be equal to the buoyant force in order for this to stay at rest floating here. So if the buoyant force is 294 newtons, then the weight of the wood is also 294 newtons. Well, what about the weight of the displaced water? Well, Archimedes' principle tells us that the buoyant force is equal to the weight of the displaced water. So in this case, the displaced weight is also equal to the 294 newtons. Let's talk about apparent weight now. If any of you have ever tried to pick up a big heavy stone out of a lake or a river, you may have noticed that it's much easier to pick it up when it's in the water than it is to get it up out of the water. And that's due to the buoyant force kind of helping us out to pick it up. So here I have this stone as a weight downwards, and the buoyant force is going to help counteract how heavy it feels by helping us lift it up. So this is called apparent weight. So the apparent weight is equal to the actual weight of the object. That's not changing. The force of gravity is not changing. But we can subtract the buoyant force, which is kind of helping us pick it up. So let's say I have a 300 Newton stone with a volume of 0.025 meter cubed. It's at the bottom of a pond. What is the stone's apparent weight? So apparent weight is the weight of the object minus the buoyant force. Well, here the weight of the object, that's just 300 newtons. But now we got to use our buoyant force equation to calculate what the buoyant force is going to be. Well, that's just rho Vg. Rho is the density of water, 1,000. V is the volume displaced. Well, I didn't tell you the volume displaced. I told you the volume of the stone. But because it's fully submerged, the volume displaced of water is the same as the volume of the stone. And then multiplied times g, which is 9.8. And we arrive at a buoyant force of 245 newtons. Well, we still want to calculate what the apparent weight is. That's just the weight, the 300, minus the buoyant force, 245. And that gives us an apparent weight of 55 newtons, which is much less than the actual weight of the object, making it much easier to pick up. Well, it's still in the water at least. Here I have a pressure tank, and on this pressure tank, it records a pressure of 0 psi. Now, psi stands for pounds per square inch, which is the units that we use, the imperial units we use in the United States. We're always going to use pascals in this class, but you may have heard psi. So this also records a pressure of 0 pascals. Does this mean that there is 0 pressure inside this pressure tank? That there's no air inside, it's a complete vacuum inside? Well, no. This is what's called the gauge pressure. And the gauge pressure is just the pressure difference between the atmospheric pressure and the pressure in a container or in the pressure in a fluid. So the absolute pressure, the real absolute pressure in a fluid is equal to the gauge pressure plus the atmospheric pressure. So let's go back to this book example. We measured the pressure the book applies to the table, and we got a value of 56 pascals. Is this the gauge pressure between the book, from the book to the table, or is this the absolute pressure from the book onto the table? Well, we didn't calculate or didn't take into account the air pressure also being applied to the table. So this is the actual gauge pressure that the book is applying to the table. So it's applying 56 pascals in addition to the atmospheric pressure that's already being applied there. So we can calculate what this absolute pressure is going to be. We can just add the gauge pressure plus the atmospheric pressure. The gauge pressure is 56, the atmospheric pressure is 101,000. So we arrive at 101,056 pascals is the absolute pressure from the book and the air onto the table. So now let's talk about Pascal's principle. So here I have this U shape of water, and instead of this being open up to air, I have this rubber stopper on both ends. Now, the pressure inside of a fluid is equal to rho GH plus P0. Now this P0, this is the pressure at the surface of the water. Normally this is just atmospheric pressure, but what if we have this rubber stopper and we actually increase the pressure by pushing down on it? By increasing this pressure, that's going to increase the pressure in the fluid, which then is going to increase the pressure on this side. So Pascal's principle states that the increased pressure on one side of a fluid is going to result in an increased pressure on the other side of the fluid. Now, what's neat about this is pressure is dependent on the force and area. So by changing the area of these two sides of this loop of water, we can actually change how much force is applied to the other side. So for instance here, if I apply a force F1 to area A1 on this side, it's going to result in force F2 with area A2 on this side. So from Pascal's principle, these two pressures must be the same. The pressure on this side must be the same as the pressure on that side. And pressure is force over area. So we get force 1 over area 1 equals force 2 over area 2. And this is another version of Pascal's principle. So let's use this to calculate some forces here. So here I have a very simple depiction of a hydraulic lift. So it's that same U shape of liquid here. And let's say this mechanic is pushing down with a force of 500 newtons onto this piston. And this piston has a cross-sectional area A. That's the area of the piston here. On this side, we're trying to lift this car, which is 15,000 newtons. And I want to calculate what must the area of this piston be in order for him to accomplish this. Well, we can just use Pascal's principle. F1 over A1 equals F2 over A2. We know that he applies a force of 500 newtons over an area of 0.15 meters squared. And we want to at least lift the car with a force of 15,000 newtons. What area must this be in order to accomplish that? Well, we can just plug in our numbers, like I mentioned, and we can just solve for A2, and we arrive at a value of 4.5 meters squared. These are all the equations that I've highlighted for this unit. I hope this helps. Let's get started.